controls. Okay, great. Everything good? Okay. Thanks again. I'm going to talk about a different spin, as Scott mentioned. We're working a lot on storage-centric computing for many different things, including machine learning. But today I'm going to focus on genomics and metagenomics. If you were here 2 years ago at FMS 2022, we talked about GenStore. I'm going to briefly mention that in this talk also, but we're going to talk about something that's even bigger, hopefully. Let me give you a quick background on motivation. Clearly, genome analysis can affect many things in our lives and science and medicine, etc. And there have been a lot of developments in genome sequencing, especially in the last 20 or so years. These are some high-throughput sequencers. I cannot keep up with them, frankly. These are some portable sequencers that have been developed recently, Oxford Nanopore Technologies. And sequencing cost is reducing drastically with the introduction of new technologies that can chop DNA and RNA into smaller pieces. This is the cost of human genome sequencing. It's gone down from $100 million in 2001. Right now, we're at $1,000 or so. So that's amazing. This is kind of faster than Moore's law, as you can see over here. Now, the problem is we can generate a lot of genomic data. You can imagine sequencing anything in this room. You can actually go through and sample everything in this room and figure out what's going on, right? The problem is data generation is very fast. Unfortunately, data analysis is very slow. You need to move the data around a lot, and you also need to analyze the data using special purpose machines. So we are in our goal in this research is to solve these two major problems, and we've been working on this for a while right now, since 2006 or so, and we've been writing papers. This is a tough area to get into. If you're interested, you can take a look at some of the relatively easier to understand papers that we've written on the topic, and we have some updated papers coming up. And we also build a lot of infrastructure to understand how we can actually develop better storage systems and better memory systems to actually do better. And these are some of the tools. Again, these slides are available. I'd be happy to send them to you also. And we have a GitHub where we open source essentially everything we do as much as possible. Before I go into the topic, we also have a genomics course. If you're interested in this topic, it's a tough area to get into. As I said, you can take our genomics course. It's also open source online on YouTube. Processing in memory course and storage systems course that cover a lot of these topics that I'm going to touch into today. Okay, now let's jump into the technical material. So as I said, 2 years ago, we presented in-storage genomic data filtering. We call this GenStore. I'm going to mention that briefly. You can find the paper online. You can find the talk from FS 2022. But I'm hopefully mainly going to focus on a paper that we presented last month at ISCA that looks at metagenomics in storage, which is actually a much harder problem, in my opinion. So let me talk about GenStore. So what is the issue with genome analysis? Basically, you have sequencing machines that extract fragments of the DNA sequence. And what you need to do is to match this DNA sequence to a single reference genome. That's the traditional genomics. This is called read mapping. It's the first step. And this is actually a very heavy step in terms of data movement as well as computation. And the goal is to identify these chopped parts of the genome and figure out where they match the reference genome, right? And this is this is called alignment, essentially. And you find an alignment score for each chopped piece of the genome. Now, this comes with differences. Basically, it's a computationally expensive approximate string matching problem. You need to account for the differences between the reads, these are the fragments, and the reference parts. And you may have sequencing errors and genetic variation. And this is why you need to be very accurate in identifying these differences. Okay, so what's the problem? Essentially, this is computationally expensive. And it's also data movement wise expensive. So you need to move the data from the storage system to a computation unit. People have been designing recently accelerators. So there's a lot of computation overhead because of this approximate string matching, and there's a lot of data movement overhead. So a lot of work has tackled the computation overhead. People actually do a lot of heuristics, accelerators, filters. We actually did a lot of this in 2010, 13, 15, etc. So this reduces the computation overhead because now you have a much better mechanism in terms of both software and hardware accelerators. But this exacerbates the data movement overhead. Now you're much more bound by the data movement. And that's in this work, we wanted to tackle that data movement overhead problem, essentially. And our idea was very simple. We wanted to filter the reads that do not require alignment inside the storage system. And basically, this way, hopefully, you would do a little bit of processing in the storage system and move very little data to the computation units. And the question is, how do you do that? Essentially, you need to figure out what is easier to do on the storage system, what eliminates the data moment significantly, and what you should really do on the computation units, which could be more powerful. Exactly matching reads, for example, if a fragment of a genome matches your reference genome exactly, this is a very easy computation. It's very simple XOR tree essentially, right? This doesn't require expensive approximate string matching, so it's better to do it in the storage system. Non-matching reads, if the read is significantly different from the reference genome location, then you actually can easily determine this also. So that's the idea in this work. If you do that, then the question is, of course, how you design the storage system for this. And this is a workload algorithm architecture co-design problem. You need to make sure read mapping workloads are accounted for. And there are limited hardware resources in the storage system. That's what we tackled in this original work. And this way, we were able to reduce the data moment overhead, and we got significant speed ups as well as energy reductions. You can see the numbers over there, more than 30x speed up in some cases, and around 30x energy reduction in some cases. And here, the speed up is a range because it really depends on what fraction of the things you can filter out in the storage system, right? This very much depends on the use case. So I don't want to go into the details of the GenStore design right now. You can find it in the paper. But basically, we add accelerators next to each flash die in flash control, next to each flash controller. These are hardware accelerators. And these hardware accelerators do the filtering. And only the reads that need substantial processing go to the CPU or some accelerator that's in the other side, non-storage side, let's say. Now, we needed to tackle a bunch of challenges over here. I already mentioned this, so I'm going to skip this one. Basically, we designed two different types of accelerators. One is for exactly matching reads, and one is for non-matching reads. I'm going to briefly talk about exactly matching reads, because even exactly matching reads require some good way of accessing the SSD so that you can stream the data out nicely from the SSD. So we wanted to eliminate the random accesses per read, and we wanted to utilize the limited DRAM capacity inside the SSD without increasing that. So we need to design data structures that way. And this requires your reads to be the same size as your k-mers. And also we do some sorting so that we can actually nicely stream data, sorted data out of the flash chips and compare them in a nice way. I have a nice animation over here, which I'm not going to go into in detail, but basically you have a sorted read table and a sorted k-mer index. K-mer is really a portion of a read. And you basically compare them in a sorted manner. And the sorted manner allows you to stream data out without, while minimizing random accesses. Again, I don't want to go into detail because this is old work. We already presented it. You can look at it in the paper. But the key is really avoid random accesses and have simple low-cost logic to do this. We also have another optimization. You don't want to really store these huge k-mers, if you will. Instead, you want to hash the k-mers so that you have a strong hash value that represents each k-mer. And this reduces the storage requirements inside the SSD as well as DRAM significantly by about 4x. Okay, there's a lot of optimization that you need to do clearly to make this work. And in the end, there's a design that we discuss. I'm going to skip this one also because there's not enough time. But if you do enough batching, etc., you can actually get significant performance improvements. This is data from 2022 presentation and paper. We compared to state-of-the-art software, state-of-the-art hardware accelerators. And at that time, we showed significant benefits. You see that depending on the read sets that you do, if you have, for example, 80% exactly matching reads, you can get significant speed ups and energy reduction. In some cases, there are some use cases where most of the reads are not matching. This actually ties into metagenomics that I'm going to talk about. In that case, you get even higher speed ups and higher energy reductions. And we showed that you could actually get this at relatively low cost in terms of hardware. In an 8-channel SSD, essentially, you get less than 10% of the cost of ARM processors that you have over there. Okay, if you're interested, there's a lot more information about GenStore, but now let me focus on metagenomics a little bit in the remaining time. So what's next here? Basically, there's a lot of things that you can do, but metagenomics is actually a fascinating topic. I'm going to mention that right now. Let me give you some background. So essentially, what metagenomics does is you study the sequence of diverse organisms. You take a sample. You can take a sample from here, and I want to figure out what's lurking there. What kind of organism is there? This is a much tougher problem. It's a shared environment. But this actually overcomes the limitation of traditional genomics because you don't need to figure out the reference genome beforehand. You don't need to know the species. You identify the species this way. And people have shown that this has led to groundbreaking advances in precision medicine, understanding, for example, understanding outbreaks, etc., and microbial diversity of an environment. Now, the way this works is you take a sample, as I said. You don't know what species are there in the sample in advance. You prepare the input queries based on that DNA sequence sample, and then you try to access a huge database or huge set of databases to identify which of the known organisms that these samples may belong to. This is called presence-absence identification, and this is where you get the storage-intensive step. These databases can be hundreds of terabytes or even larger, actually. And things are becoming larger and larger as we accumulate more information about different species. And then you can actually do abundance estimation, which is another step where you figure out, the sample that I identified over here is 5% human, 50% something else, 60% something else, etc. So you can do a lot of analyses after this. Actually, there are a lot of studies that people have done. For example, there's a famous study that people have sampled the DNA or RNA of organisms in the New York Metro, New York subway, and they figured out that what's lurking in the New York subway. You don't want to touch anything in the New York subway, basically. That's the key takeaway over here. Okay, so we actually analyzed the state-of-the-art software tools using both performance-optimized and cost-optimized SSDs. If you eliminate the I/O overhead completely from the SSD, you get very large speedups. This is ideal, of course, right? You can see that, especially compared to cost-optimized SSDs, you get 40x almost speed up. And this speed up increases as the database size increases. You can see that our database sizes are actually very small, 1.4 terabytes. But it's good to show, even with that small database, you get significant improvements. And if you actually do accelerators on the CPU side, computational side, these overheads become even larger. So we're talking about numbers greater than 100x, etc. And these numbers are going to grow. Now, you can say that, oh, I'm going to avoid these things with software techniques. People have tried that. It's very difficult if you want to keep accuracy. If you want to get rid of accuracy, then it's very easy, of course. Don't do processing, right? It's relatively simple. And people also say, oh, why don't we actually have everything in memory? Why do we have storage? Sometimes academic reviewers have this, unfortunately. And we have to say that that's unreasonable. Basically, you cannot just have everything in memory. Okay, our goal in this work was to do metagenomic analysis, improve its performance and energy efficiency by reducing this large data movement overhead from the storage system in a cost-effective manner while keeping the accuracy. We don't want to get rid of the accuracy, essentially. So there are challenges here. Essentially, we want to do processing inside the SSD. Unfortunately, even existing analysis tools cannot run easily because of the long latency of NAND flash chips, limited DRAM capacity, and limited DRAM bandwidth that we have. If you want to port existing tools, you get very bad performance, essentially. So that's why we designed Megas, essentially. This is the first in-storage system for end-to-end metagenomic analysis. It's a cooperative in-storage processing, meaning you have a hardware-software co-design between the host CPU as well as the storage system. We divide tasks between them, and we parallelize tasks between them. In the future work, you can actually parallelize the task in in-memory processing also in the CPU as well as the DRAM, as well as the SSD, but we're working on that. So we essentially accelerate these 3 steps that I mentioned earlier. I'm going to briefly mention how we do that, but let me give you the very overall. This is a full system level work. You have a hardware-software co-design. You need to partition the tasks and map the tasks such that each step executes in its most suitable system. We decided step 1 executes on the host system, step 2 and 3 executes on the SSD, but going forward, step 1 can execute in the memory side of the host system as well as the CPU. And then you need to have data and computation flow coordination. You need to reduce the communication overhead and reduce the number of writes to flash chips, and we have mechanisms, data structures to do that. You need to enable storage-aware algorithms, meaning enable efficient access patterns to the SSD so that you're streaming out of the SSD and minimizing the random accesses, similar to the methods that I mentioned with GemStore, but a little bit different. And we need to have lightweight in-storage accelerators so that we can minimize the SRAM and DRAM buffer spaces that are needed inside the SSD with minimal modifications. These are hardware accelerators. And also, we need to have a data mapping scheme and flash translation layer. We modify that also so that we can specialize to the characteristics of the metagenomics analysis application while leveraging the full internal bandwidth of the SSD. Again, there's a lot to digest here. It's all in the paper, but I'm not going to focus on everything. I'm not going to go into detail since we have limited time. Let me quickly talk about step 1 briefly. So we decided step 1 executes on the host CPU, and we employ sorted data structures to avoid expensive random access to the SSD because host CPU performance is still determined by the SSD significantly. So we do a lot of sorting first, offline sorting. The reason we execute this on the host CPU is because of the sorting, you need large DRAM. And we don't want to modify the SSD significantly currently. Going forward, that may be a different thing. Going forward, we may need actually larger DRAMs if you want to do more sophisticated computation in the SSD. But and we also wanted to have fewer writes to NAND flash chips in this first processing steps. And we also can overlap step 1 and the other steps that are executing on the SSD. Okay, I think I've already discussed the major things, but we improve the performance and lifetime of the SSD by doing this on the host CPU. This is the design very quickly. We independently partition the reads or k-mers. K-mer is a k-length string essentially, but based on their alphabetical range in the host DRAM. And you can overlap operations on different partitions this way and exploit the parallelism inside the DRAM so that you get high performance on the host CPU. Okay, let's talk about step 2. This is where we actually do processing inside the SSD significantly. The goal of the step 2 is really to identify the common substrings between the query substrings and the database substrings. We want to retrieve the species IDs of the common substrings because you really want to figure out what species does this substring belong to, right? And this is a step where you do a lot of scanning of the database. So there's a lot of large data accesses with very low reuse, and this is a great fit for computational storage. And there's very lightweight computation, as I said, because this matching is relatively easy, similar to GenStore earlier. So to be able to do this, we need to leverage internal bandwidth of the SSD efficiently, and we want to avoid expensive hardware inside the SSD, meaning large DRAM bandwidth or capacity or costly logic units. So how do we do this? Again, at a high level, if we actually bring everything to the SSD DRAM and the processing, do the comparisons and matching from the SSD DRAM, this is not good because your bandwidth bottleneck in the SSD DRAM. So what we do is we directly process on data streams that are coming out of the flash chips. We have buffering and accelerators, intersection accelerators, so that we actually get the data and do the processing inside the SSD controller with as little logic as possible. And then eventually we write the data results into the SSD DRAM. These are the common k-mers, meaning things that we found common between the sample and the reference genome in the database. Again, I'm going through this at a high level, but there's a lot of detail, and we actually open source a lot of the RTL, etc., in our work. Then you need to actually figure out the species ID. This is actually interesting. I'm not going to go into a lot of detail, but how you map a substring to a species ID matters a lot. You could do a table-based approach that looks like this, and a single substring may actually map to many species. This is very space inefficient, and it's not a good fit. And then there's a very space efficient version of this where you actually have linked data structures, graph type of data structures. Unfortunately, that leads to a lot of random accesses. We develop a continuum over here, and we develop something called k-mer sketch streaming, which is space efficient and also mostly streaming, but it's not as space efficient as random access data structures. So in the end, we get a lot of space efficiency with streaming accesses. And I refer you to the paper to understand how you do it. In the end, I think all of these designs are there to reduce the random accesses while minimizing the logic and space overheads. Okay, I'm not going to talk about step 3. This is very interesting, but we don't have time for it. But it's a fascinating step also. If you're interested, you can take a look at the paper or talk to me afterwards. So we compare this work. We use the simulators that I mentioned earlier in the talk to do the simulation. We compare it to both software approaches that are published in respectable genome biology venues, for example. And we also use multiple different SSD configurations, cost optimized and performance optimized. We do different metagenomic analysis tasks, and we have different kinds of metagenomic samples because genetic diversity of a sample may be significant and genetic diversity may not be significant. If the genetic diversity is actually very significant of the sample, then your task is much harder because you need to identify many different types of species in your sample. Okay, let me give you the key results. So these are the key results compared to performance optimized and accuracy optimized baselines. Performance optimized baselines lose accuracy. I'll remind you that. So compared to performance optimized baselines, we get significant speed up. And compared to accuracy optimized baselines, at the same level of accuracy, we get even higher speed up, around 15x, as you can see. And you can see that on both cost optimized and performance optimized SSDs, we get significant speed up. This was the cost optimized SSD. This is the performance optimized SSD. Compared to processing in memory, we actually do much better also. Again, I'm not going to go into details, but there's work that we're doing to actually combine in SSD and in memory processing. Energy consumption benefits are also significant. This is an accuracy optimized baseline. Compared to that, we do 15x improvement while keeping the same level of accuracy. And there's a lot more results in the paper about area and power consumption, which is not bad, as you can see, based on this picture. Let me mention one thing before I conclude. Essentially, this is system cost efficiency. We also wanted to understand how does it affect overall system cost efficiency. For example, you may have a cost optimized system with a simple SSD or cost optimized SSD, low bandwidth, and a very small DRAM, 64 gigabyte DRAM for the host. And you may have a performance optimized system, which is very costly, expensive SSD and 1 terabyte of DRAM. If you use Megis on the cost optimized system, you actually outperform the performance optimized system by about 7x. This is very significant because by doing in-storage processing, you can actually reduce the cost of your system. And this may be actually something that people may want to consider. Essentially, you can improve cost efficiency, and you can enable accurate metagenomics more accessible for wider adoption. There's a lot more in the paper, like we varied a lot of sensitivity, etc. You can find online. And the paper is online, and the source code is also open source. Okay, I'm not going to go through the slide. Basically, summarize everything I said. But at this point, I'll conclude. I'd be happy to take any questions and discuss future work at any point. Thank you.
All right, we've got a few minutes if there's any questions for our three speakers. Happy to hear it. Adding, like I did on the other two, a personal color, if you will, this presentation. It's great to see it expanding beyond our traditional market segments that we deal with here at Flash Memory Summit, and a big emphasis on the cost savings aspect. It's not about always doing it faster. It's all about doing it better, and it can always end up being cheaper too. So I appreciate the depth of information presented. And I think he set an all-time record for the number of slides in that FMS deck, and how to download it, a little over 130. So I do appreciate that you put in the effort to put that together. So thank you very much.
Thank you very much, Scott. Thank you.
If there's no other questions, we'll go ahead and wrap up a few minutes early and let you head to your next section. So.